In this lesson, we're looking at first-order differential equations in the form dy dx is equal to a function of y. In this scenario, when we're looking at solving these differentials, the idea is that because it's a function of y, in order to be able to perform the integrations, we need to bring the function of y over to join the rate of change of y. So that means that we're looking to rearrange it into the form 1 on f of y dy is equal to, in this case, this will look like a 1 dx, and again, we've got a pair of integrals. So much like when we're in the form dy dx is equal to f of x, and it's about ensuring that when we separate the differential, the dx is with the function of x. When we have a function of y, it's ensuring that when we separate that differential, that dy, the change in y, is with that function of y. So after that, again, the idea is that we can group the differential with the functions. We can then perform the integration, and then we can isolate the variable that we're trying to create a function with respect to. All right. So this will be a pretty quick lesson. We'll look at a couple of examples. The first example, we have dy dx is equal to 2y plus 1. So dy dx is equal to 2y plus 1. Now, we can think of this whole thing as a bracketed function of y. So that means we're looking at it as 1 multiplied by this function. When we separate the differential then, we want to bring this 2y plus 1 across, but we also want to bring the dx across. So we've got 1 on 2y plus 1. So we've divided by the function of y, dy, and that will be an integral. And on the other side, we'll have our 1 dx, and that will be an integral. Right, so we end up with two simple integrals. Now we should know this one here, we can use that special quotient rule. We're looking at the numerator being the derivative of the denominator, so we can use a natural log. So in order to get this numerator to 2, we can say that's 1/2 the integral of 2 on 2y plus 1. So we multiply by 2 and divided by 2, so it's still balanced. And then this becomes, and then this stays as our 1 dx. Now to perform both of these integrals will be nice and straightforward. We have 1/2 ln 2y plus 1, and the integral of 1 is x plus c. We can get rid of this 2, so we multiply this 2 through, and we've got ln 2y plus 1 is equal to 2x plus c. Don't need to change that constant value because that will be worked out later. And then finally, to get rid of the natural log, we can use base e. So we now have 2y plus 1 is equal to e to the 2x plus c. Now, that also means it's e to the 2x multiplied by e to the power of c. And we can let e to the c be some parameter a. So now we have 2y plus 1 is equal to a e to the 2x. Now to isolate y, we can subtract 1, divide by 2, and we end up with y is equal to a e to the 2x, subtract 1, all on 2. Right, so there it is. There's our general solution for dy dx is equal to 2y plus 1. When we look at b, we've got dy dx is equal to e to the 2y. Now we want to take the same approach. Because this is e to the 2y, it's with respect to y, we want to bring this over, and we want to group it with that change in y. So we can make this 1 on e to the 2y dy, and on the other side we're left with that coefficient of 1 dx. Now, in order to find this integral, we want to apply our index laws, and this is the same as writing e to the negative 2y dy, and the integral of e to the negative 2y is negative 1/2 e to the negative 2y, and we've got x plus c. So now if we want to go about isolating y, we can multiply by negative 2, so we have e to the negative 2y is equal to negative 2x plus c. Again, c will remain unchanged. We can use our natural logarithm here, so we have negative 2y is equal to ln of negative 2x plus c. And therefore y will end up being negative 1/2 ln, and we'll make this c take 2x. And there we have it, there's our general solution for b. When we move on to look at c, and the original differential equation is dy dx is equal to square root of 1 take y squared. We first of all want to group this function of y with the dy, so we've got 1 on square root of 1 take y squared dy, and it will be equal to, again, that coefficient of 1 dx. Now this is a pattern that should be familiar. We're looking at 1 over the square root of a squared take y squared dy, which means it's going to be arc sine of y on 1, and on the other side it will be x plus c. So we have arc sine of y is equal to x plus c. Now, so we have to isolate y, as it is the dependent variable. To remove this arc sine, we need to take the sine. So we have y is equal to sine x plus c. And there is our general solution. So now to look at the last example. We have dy dx is equal to 1 take y squared. We'll go through the same process, and we'll group the function of y with our change in y. So we've got 1 on 1 take y squared. Dy is equal to 1 dx. So we treat that as if it's a bracket and divided it across. Now hopefully you can see this is a difference of perfect squares. So it's integral of 1 plus y and 1 take y. Dy is equal to the integral of 1 dx. Now, recognizing that this is going to take an integration by partial fraction approach is important. We need to consider this 1 on 1 plus y, 1 take y, in the form a on 1 plus y and b on 1 take y. So we end up with 1 is equal to a lots of 1 take y plus b lots of 1 plus y. And therefore, when y is equal to 1, we get 1 is equal to 0a plus 2b. b is equal to 1/2. And when y is equal to negative 1, we get 1 is equal to 2a and 0b. So therefore, a is equal to 1/2. So if we now fit this into our solution, we've got the integral of a on 1 plus y, which means we've got 1/2 on 1 plus y, and b on 1 take y, so that means we've got 1/2 on 1 take y. Dy is equal to integral of 1 dx. We can take out this common factor of 1/2, and we've got 1/2 integral of 1 on 1 plus y plus 1 on 1 take y dy, the integral of 1 dx. It would make it easier to get rid of this 1/2 and just multiply it across. So now we've got 2 dx. So now the integrals are pretty straightforward. Integral of 1 on 1 plus y is ln 1 plus y. The integral of 1 on 1 take y is negative ln 1 take y. And on the far side we have 2x plus c. So we'll have, using our log laws, ln 1 plus y over 1 take y is equal to 2x plus c. And that simplifies down to 1 plus y over 1 take y is equal to e to the 2x plus c. Now if we can say that a is equal to e to the power of c, then we end up with 1 plus y on 1 take y is equal to ae to the 2x. Now, our last step is to get the explicit function where y is isolated. So we have 1 plus y is equal to ae to the 2x, 1 take y. Now if we expand this and we group the y's, we've got y plus yae to the 2x. And on the other side, we've got ae to the 2x take 1. When we take out the common factor of y, we've got y and then 1 plus ae to the 2x. And equal to ae to the 2x take 1. And then finally, when we isolate y, we've got ae to the 2x take 1. Divide by the bracket, which is 1 plus ae to the 2x. So here we have our general solution. It's good to think, if you're trying to find a specific solution, at which point is the best point to work out what the parameter is. Now, in this case, I think that this point would be the best. If you have a value for x and y, you can easily work out what a would be, and therefore you're set with your parameter from that point on. So it's good to think back through all of your problems, which is the best point. Where should I calculate my parameters if I'm given extra information? Okay, so that concludes the lesson. That's looking at the first order differential equations, ODEs, when we're in the form dy dx is equal to f of y. Thank you.